Okay, this is the 7th video in the series on molecular substances, and in the previous videos I've laid the groundwork for the fact that these are forces between molecules, and then we have literally walked through the different types of intermolecular bonds or intermolecular forces. And in the previous videos we talked about the hydrogen bonds, we talked about dipole forces, we talked about London dispersion, and finally now we're going to focus on what are called the ion dipoles. Now the ion dipole forces, these are unique, a unique type of force because it involves the interaction between an ion that is dissolved in some type of substance and the molecules that have to interact with that ion. So this is and I'm going to abbreviate the IB that occurs between a dissolved ion and the dipole of the substance the ion is dissolved in. All right, and the model system that we're going to look at for this is going to be, we'll start with taking table salt and dissolving that salt into water. And if I write what's technically called the ionization equation, the ionization equation, it's going to look like this. Now, some terms, all right, to just make sure we're all on the same page. When I use the term ionization equation, what that means is the chemical reaction that produces ions. The chemical reaction that produces ions. And I'm forgetting myself here. So we're producing sodium ion and chloride ion, all right? And we show this going from the solid ionic crystal. All right, this is an ionic crystal. Imagine that in your salt shaker, going to basically aqueous environment, which means dissolved in water. Now, so two very important definitions. The first being an ionization equation is a reference to the formation of ions. Usually in chemistry, when we're writing an ionization equation, it's a reference to the fact that we're taking that salt, whatever it is, in this case it's table salt, and we're dissolving it into water. All right, and then the second thing is, this has to do with a rule of thumb. If you have an ionic compound and you add it to water and it dissolves, then that compound has to be separated into its ions. All right, that's a rule. If that doesn't happen, then that compound will not dissolve in the substance that you're trying to dissolve it in, and the material is simply going to drop to the bottom of the container and pile up on the floor of that container. So we have an ionization equation here. Now, to understand the ion dipole interaction, what's important to realize here is that this, in a university level general chem course or an advanced placement course or even a high school chemistry course, where this is important is in dissolving ionic substances in water, because the principle that we're about to apply here and look at happens for any ionic compound that dissolves in water. All right, so let's take a look at the difference between the products of this process, these being the products, and the starting material. So in the starting material, this is actually a crystal that has oppositely charged particles on it that range throughout the material like this. All right, and you can imagine a situation where that crystal extends in all directions. In the case of the ions that are dissolved in the water, they are going to be present in what are called hydration spheres. So the sodium ion is going to look like this, and it is going to be surrounded by water molecules, which are going to be oriented so that the negative oxygen faces in towards the positively charged cation in this case. So we've got our little negative oxygen here that is lined up facing in towards the positively charged cation. All right, now let me get the rest of the water molecules around here. So because the cation is going to have to be completely surrounded by the water molecules. All right, and so we're just going to go around this thing and draw these in like this. And let's see, 1, 2, 3, 4, 5. I only have 5 of them in here, so I'm going to squeeze another water molecule in here so that there's 6 of them. And sorry about the artwork. This is just the way it's going to have to be. So we've got our little negative charges are faced in towards the positive cation. All right, and we again, there's a name for this. We call this a hydration sphere. Hydration sphere. And any ionic compound that's dissolved in water is going to have the ions in hydration spheres. All right, now similarly to the sodium cation, the anion is also going to be hydrated. The difference is going to be that the water molecules are going to be faced inward like this, so that the hydrogens now, the partially positive hydrogen ions are going to be, or the partially positive hydrogen atoms are going to be faced in towards the negative charge on the chloride, more or less like this. And again, my artwork may not be there should be 6 of them here. You know, I'll just squeeze another one in here like this. It's again, the artwork here is not the best in the world, but now we're going to have our little positive C faced in towards the chloride anion. So there's a difference in the orientation of the water molecules. Now, to finish the lesson here, the name of this thing is called an ion dipole because here is the ion, and it's going to have a charge of a positive on it or a negative on it of some magnitude. And here is the dipole. And if just to finish, the strength of this interaction between the cation or the anion and the water molecule is the strongest of all the intermolecular bonds that we've talked about. So this is the strongest of all IBs.